Alright, this is the first concept, or I should say first video lesson for this unit that you're going to be watching. We're going to be focusing on the Arrhenius theory for acids and bases. Alright, an Arrhenius acid is a substance that releases positive hydrogen ions, which are referred to as protons. And this is the only positive ion in the solution is this hydrogen ion. And that's how we would define an Arrhenius acid. And just realize that not all substances containing hydrogen are acids. You can look at table K in your reference tables to see a few examples, especially when hydrogens are covalently bonded directly to carbon. This usually indicates that you have an organic molecule or a different type of molecule and not an acid. And we'll talk a little bit more about that in class tomorrow. Alright, so what happens is we have a hydrogen atom and it loses an electron. So this hydrogen or positive hydrogen ion is really just a proton, and a proton actually can't exist alone in water. It usually ends up attracted to an unshared pair of electrons on H2O. So you can see down here in this equation that we have this proton, so a positive hydrogen ion, that is then going to bond with H2O to make what we call the hydronium ion. So frequently you're going to see me kind of interchange, or you might see on worksheets, sometimes referred to as the proton that we're looking for to identify an acid, but also realize the hydronium ion, H3O+, also identifies acids. For example, when we have HCl, and I'm sorry, that should be a lowercase l there, when it dissolves in water, its acidic properties are the result of those protons produced, or the positive hydrogen ions. So when HCl is dissolved into water, it's going to break up into the two ions that make it up. We have again the positive hydrogen ion, this gives it the acidic properties, and the extra chloride ion, which this we would kind of consider a spectator ion. It's not really going to influence any of the acidic properties. We're more worried about the positive hydrogen ion. Now for Arrhenius base, how we define it is that it's going to be releasing hydroxide ions in the aqueous solution. And remember, OH has a -1 charge. And also keep in mind, just like when we talked about Arrhenius acids, not all compounds that contain OH are bases. So you have to be very careful. And again, when OH is connected to a carbon chain, it actually makes what we refer to as an alcohol that does not ionize or dissociate. So just something to keep in mind, being very careful of when you identify bases. And again, you have table L in your reference tables that you can always refer to for some examples. And just like we were looking at for Arrhenius acids, we can also look at a base to see how it dissolves in water. And in this common example of sodium hydroxide, when it dissolves in and dissociates in water, we end up with a sodium ion, plus we have our hydroxide ion. So this sodium ion, again, is we kind of look at is what we will refer to as a spectator ion, and we're more worried about the OH ions produced, because again, that's going to give it its basic properties. Acids and bases can neutralize each other, and when they react, they're going to form what we refer to as a salt, and they're going to produce water, H2O. Our general equation is, again, we're looking at having an acid and a base, and we're going to be producing water and a salt. And this is going to look exactly like if we were to complete a double replacement reaction. In class, when we talked about concept A, we worked with single replacement reactions when we were reacting a metal with an acid. Now we're going to be looking at making a double replacement reaction, which is going to help us produce successfully this water and salts. So for example, we have this example up at the top, and this NaF atom, so sodium fluoride, is what we refer to as the salt. And if you look, the positive ion, the sodium, comes from our base, okay, over here, and the negative ion, the fluoride ion, is going to come from my acid. And again, I've been using this term spectator ions. They're there, but they just don't do anything. They're not going to participate in the actual neutralization. So again, when we're creating the salt, the positive ion comes from the base, the negative ion comes from the acid. And at this point, you should be able to identify that HF is your acid and sodium hydroxide is your base. So here's that example if we or a little bit different of an example that we're looking at. We have sodium hydroxide, so NaOH, plus our acid, hydrochloric acid, HCl. And we've broken it up into all the ions that it would dissociate or ionize into in water. And when they react, we're going to see that we form H2O. And again, sodium and chloride ions are there. They're spectator ions, so they're not going to actually do anything. We're more worried about the reaction between the hydroxide ions and the positive hydrogen ions to make H2O. And you're going to see me write H2O as HOH frequently throughout this unit. It just makes it a little bit easier when we're looking at writing, especially these double replacement reactions. So a little bit more about how we're going to do these reactions. When the acidic and basic solutions are mixed, the positive hydrogen ion of the acid and the hydroxide ion of the base are going to combine to form water. And then we're going to see that our negative ion of the acid and our positive ion of the base are going to come together to form the salt. And this is just defined as the ionic compound that's formed by the acid-base neutralization. And again, I've referred to the fact that water I'm going to be writing as HOH. All right, so let's just look through and work through two examples of these neutralization reactions. So I'm first going to be looking at creating water. I'm going to take my positive hydrogen ion from my acid, and I'm going to take my hydroxide ion from my base. I'm going to form water with those. I'm then going to go ahead and look at taking my negative ion of my acid, the anion, and then my cation of the base, so my negative ion of my base, and I'm going to then form my salts. Now, one thing to remember is that while the order looks like Cl and K, because potassium K is my positive ion, that should always be written first. So this goes back to our formula unit that you may need to brush up some of your skills on. So I'm going to go ahead. These each had a 1 charge, so potassium was +1, Cl was -1, so they balance out, just being 1 and 1. And that's it for that part. And again, of course, if we're balancing this, you would need to make sure that everything was correctly balanced, which is in this example. All right, last example, again, I'm going to first create water, HOH. Okay, I've taken it from my hydrogen, positive hydrogen ion from my acid, and my negative hydroxide ion from my base to make the HOH. I'm going to then go ahead and look to take my positive ion from my base and my negative polyatomic ion here from my acid. And remember, I'm going to put the positive ion first, followed by the negative ion. So I should form Li2SO4. And again, how we got this formula, I'll review a little bit quickly in class tomorrow, goes back to our formula unit. Li is +1, SO4 off a table, E is -2, so I had to have 2 Li's. And then before you leave the equation, make sure you go and balance it. So I had to put 2 for the coefficients where you see on the screen. Okay, well that's it for Arrhenius acids and bases and how to write neutralization reactions, and we'll be continuing practicing this in class tomorrow.